Hello, today we're going to talk about section 2.3, subatomic particles. Subatomic particles are simply the parts that are smaller that make up the atoms. So we have the electrons that orbit to the outside of the nucleus, and then we have the inner central nucleus made up of protons and neutrons. First was the discovery of the electron. By the late 19th century, the concept of an indivisible atom, as proposed by Democritus and John Dalton, was seriously being questioned because electricity could have effects on atoms. Then it hinted that they had some sort of electrical nature. In 1897, English physicist J.J. Thomson used a cathode ray tube to prove the existence of electrons. He showed that they have a negative charge and that he could figure out the ratio of the electron's charge to the overall mass of an atom. And then in 1909, American physicist Robert Millikan was able to determine the charge of an electron with his famous oil drop experiments. So here we've got a very short little video from YouTube about J.J. Thomson's cathode ray tube experiments. So he had this cathode ray tube that would move electrons across in like a beam, and it's going to show on here two electrical plates. So one up here is going to be positively charged and one down here is going to be negatively charged, and these electrons, but opposites attract. So electrons which are negatively charged, they're going to get closer to the positively charged plate. So let me see if I can get this to play.
Until the late 1800s, scientists believed that atoms were indivisible, meaning that atoms were the smallest unit of matter and could not be broken down any further. But in 1897, J.J. Thomson's experiment changed that thinking. Using a cathode ray, Thomson discovered a new subatomic particle. The experiment was simple: a glass tube filled with a vacuum, two metal electrodes, and a high voltage applied across them. This created a beam called a cathode ray. Now here's the key: when Thomson applied an electric field to the apparatus, the beam bent towards the positive charge. Thomson hypothesized that a cathode ray is a stream of tiny negatively charged particles. He then determined that these particles are incredibly tiny. He compared the charge to mass ratio to the fundamental charge of an electron and found the mass of an electron is 9.11 times 10 to the negative 34 kilograms, about 1,800 times smaller than an atom. This discovery showed that atoms are not indivisible, they're made up of smaller particles, and we now know that these particles are called electrons. Thanks for watching. If this video helps, please like it and subscribe to the channel.
Okay, now his calculations are beyond the scope of this class, but I just wanted to show how that he showed that they are negatively charged, because otherwise they wouldn't have moved toward the positively charged electrical plate. Now, next, Robert Millikan, who was an American physicist, he did this oil drop experiment to show, he was the one who calculated the exact, or not the exact, but he could calculate what the charge of an electron was and also the mass of an electron. So here is another short video.
In a series of experiments carried out between 1908 and 1970.
Well,
in a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay, so again, that mathematics got very complicated, and we're not going to try to discuss that. But between J.J. Thomson and Robert Millikan, they were able to calculate the mass of an electron and also determine the charge of electrons. So the mass of an electron is 9.1094 times 10 to the negative 28 grams. So that's 27 zeros in front, or a decimal, and then 27 zeros and then a 9, grams. So that's a very tiny amount. Next was the discovery of the proton. So if atoms are electrically neutral, yet they contain negatively charged particles called electrons. So maybe there are positively charged particles also. So that's what they were thinking. In 1898, a German physicist, Wilhelm Wien, and British physicist J.J. Thomson, they discovered protons. So the protons turned out to have exactly equal but opposite positive charge as the electrons did. So one proton is positive and one electron is negative, and they cancel each other out because they have exactly the same equal and opposite charges. Now, after the discovery about that there are protons, or that there's a positive charge, J.J. Thomson came up with this next model of an atom. So we have John Dalton and Democritus's atom earlier. It was basically a solid sphere or like a marble. J.J. Thomson's model, he changed it to be more, he called it a plum pudding model. So there's this bigger circle of positive charge, and then there's these little speckles of tiny negative electrons embedded all throughout, like raisins in a pudding. Now, in 1911, British physicist Ernest Rutherford, Hans Geiger, and Ernest Marsden, discovered that protons were actually not in the plum pudding model. They're located in the nucleus of the atom, and their experiments were the gold foil experiments. So here's a picture of an earlier time before they did their gold foil experiments. But on the left is Ernest Rutherford, and on the right is Hans Geiger in their laboratory in Manchester, at Manchester University in Manchester, England, around 1908. So in these gold foil experiments, if the plum pudding model was correct, when he has this little particle shooter, so you can think of it as like little tiny bullets that could hit protons. I mean, so if the plum pudding model is correct, they should be able to shoot these tiny particles through atoms, through layers of atoms, and it just goes straight through, because they knew that electrons were so tiny, and that they shouldn't block the little particles that they're sending through. So on this on their setup over here, this little square in the middle is a sheet of gold foil that they chose gold because it can they can fix sheets that are really thin. So they tried to make these sheets of gold be as close to like one atom thick as they could. So it's extremely thin. They don't want to be shooting through lots of layers of atoms. They're trying to just shoot through 1 or 2 layers of atoms. So here's a short video, or it's not a, it's just a, well, let me see. It's not a video. It's just a GIF that's supposed to play. Let's see. Okay. So as you can see, let me play it one more time. The particles, when they're coming through here, they expected it to go straight through and hit right over here. But if you watch what happened, some of them do, but some of them go back and boing, back here, almost like it's almost 180 degrees. It's like 170, really large angles anyway. So let me play it one more time and you watch. So they thought they'd all land back here, but they don't. So some of them are popping up back this way. So that showed that that model didn't really work very well. So they were getting large angle rebounds. So that suggested that there was something hard and concentrated in the center, which they later guessed is the nucleus. So there's lots of space in here where it can go through, but then there's one hard core in the middle that if it hit that part, then it made it bounce back. Whoops, I don't want it to play that again. Hold on. Okay, so this series of experiments disproved J.J. Thomson's plum pudding model. They had to go back to the drawing board a little bit, but then they decided, since it had that place that was causing their little particle bullets to rebound, that it had something hard. So they made they decided it was like the protons were in a nucleus. So Rutherford proposed the planetary model of the atom. And then the mass of one proton is 1.673 times 10 to the negative 24 grams. So third, the last to be discovered was the neutron. So protons alone did not account for the size of the nucleus. So they couldn't figure out, they knew something else was in the nucleus besides just the protons. It was larger than just what they could calculate was protons. In 1920, Rutherford proposed the idea of a neutral particle. And then it was 12 years later, in 1932, before another English physicist named Sir James Chadwick was able to demonstrate the existence of neutrons, and he was able to calculate their mass. So the mass of one neutron, oh goodness, hold up. Make that go away. Drag that up. There's some way I can, there's a way I can drag it to the top. Okay, now it's going away. Okay, the mass of a neutron is 1.675 times 10 to the negative 24. So it's ever so slightly larger than a proton, but it's very, very slightly. They're almost exactly the same size. Then here's a timeline from your book, table 2.6, and it just has the different progression of discoveries for the subatomic particles of an atom, and then it shows things that are going on in the world on the right hand side. So here's J.J. Thomson determining information about electrons, and then here's the discovery of well, more about the electrons and the beginning of the protons, and here's when they discovered the protons, and here's when they discovered the neutrons. So this chart, table 2.7, has the 3 subatomic particles, the electrons abbreviated by E with that little negative sign showing its charge. Protons are just a lowercase p, and neutrons a lowercase n. And it shows their mass. So again, protons and neutrons are so similar in size. I mean, it's just barely anything different. So they're almost 1-to-1 in this, equal in size. The electron is way smaller. Notice the 10 to the negative 28th power, and the others are 10 to the negative 24th power. So the more negative it is, the smaller it is. So there's a 2,000 difference between their sizes. So an electron is 2,000 times smaller than either a proton or a neutron. But now on the right-hand side of the chart, we can see how their charge compares. So electrons are negative 1.6 times 10 to the negative 19 coulombs, and protons are positive, the same number, but positive 1.6 times 10 to the negative 19. Now, we don't have to know this, they're just in a ratio. So we say that for every electron, it's a -1 charge, and for every proton, there's a +1 charge. So it's easier to count this way. Now, if we were going to talk about how large an atom is, and how big the nucleus is inside of how much space it takes up inside the atom, we could think about a major sports stadium. I'm not sure, maybe this is Yankee Stadium, I'm not sure. But if the nucleus were the size of a marble, then the outside of the atom would be the size of this stadium. So and there's all that extra space. So the electrons would be going around in the outer edge of the stadium way out here, and the nucleus would be right there. And just there's a whole lot of space inside of an atom. Now, Democritus and John Dalton were the ones thinking that atoms were solid spheres. And then we learned about the three subatomic particles. So are protons, neutrons, and electrons, are they indivisible, or can they be broken down further? And apparently they are divisible. So scientists have discovered things about other parts. They're called quarks, mesons, neutrinos, positrons, and more. So your book has a little section about quark theory. And according to quark theory, there are up quarks and down quarks. And an up quark has a charge, has a positive 2/3 charge, and a down quark has a negative 1/3 charge. So it takes 3 quarks to make a proton, and there's 2 ups and 1 down quarks. And over here, so each of the up quarks has a positive 2/3. So we've got 2 of them, so that's positive 4/3. And then we have 1 down quark, which is a negative 1/3. So positive 4/3 minus 1/3 makes a positive 3/3. So we have a net positive 1 charge. And then 3 quarks also make a neutron. Now, neutrons, are they positive, negative, or neutral? So they're neutral, right? So they are also made of 3 quarks, but different ones. There's 1 up and 2 down. So we have our up, which is a positive 2/3 charge, and 2 downs, and each of them are negative 1/3. So positive 2/3 minus 2/3 is 0. So the neutron has no charge. Now, there's other little particles, neutrinos and positrons, and others are involved in nuclear chemistry, introduced in chapter 17. And mesons, I'm not too clear about what they are, but they're made of 2 quarks. Anyway, I don't think we study about them anymore, but this is just to show that the protons, neutrons, and electrons are probably made up of a lot of other smaller pieces. But okay, that's the end of section 2.3. So I'll see you all for lab class on Friday. Thank you.